Hi everybody, sorry I had to make sure my battery was charged, so I'm a day later. So I've got 245 grams of sucrose, C12H22O11, and 1.20 liters of solution. So I'm going to change this into moles, change that into liters, and my goal is to do molarity as moles over liters. So I'll start with 245 grams of sucrose, C12, blah, 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 times 1 mole of C12, blah, 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 over, go to the periodic table. So 12 times 12.01 equals plus 22.22 plus quantity 16 times 11, close quantity, 342.34, 342.34. Again, I'm using this molar mass. So 245 divided by answer is 0.7116 moles. So here we go. 0.716 over 1.20. So that answer divided by 1.20 is 0.59. So that means my molarity for A is 0.596 molar, which is dilute because it's less than 1. 85 grams of NaOH in that solution. I'm going to change colors just to try and keep these guys a little separate. So same deal, 85 grams NaOH times dividing bar, grams of NaOH, and these numbers are coming from the periodic table. So I go to the periodic table, and I add up sodium, 22.99, plus oxygen, which is 16, plus hydrogen, which is 1.01, which is 40.00. So 85 divided by 40 is 2.125. So again, I'm going to do molarity equals moles over liters. This is 0.895. So we talked about how milliliters, you can't use it, you use liters, and move the decimal 3 places. 1, 2, 3. So my moles are 2.125 over 0.895. And I know it's going to be bigger than 1, but I know a lot of us like to have real answers. 2.37 molar. So concentrated. This is B. C. All right, 120 grams of copper nitrate and 1.45, so right away change that to 0.45 liters so I don't forget. So 120 grams of CuNO3 taken twice, that's a U. Gee whiz. Can you tell I'm writing on my lap here? So copper is 55. Oh, 63. Oh, I'm forgetting copper's molar mass. What is copper's molar mass? Oh man. It's 63.55. So copper is 63.55 plus quantity 2 times 14.01. So I have 2 nitrogens. Close quantity plus quantity 6 times 16, close quantity. So remember, you multiply that, don't add it. Equals, I get 187.57 grams of CuNO3 taken twice and 1 mole. So when I do that, I have 120 divided by 187.57, and that's 0.6390, darn it, 0.640 moles of Cu blah, blah, blah. So remember, molarity is moles over liters, which is 0.640, over my liters, which is 0.450. You're going to make it over that one. I get 1.42. So concentrated. Remember, concentrated and dilute is a relative term, so that's how it is compared to the other one. To whether there are fewer or more moles of a solute specified for solution 13 above. Which has a greater amount of moles of sucrose? 1 liter. Okay, so if I'm looking for moles, this brings us back to moles equals MV, molarity times volume. Which has a greater amount of moles of sucrose? 1 liter of solution made in 13A above, or 800 milliliters of 0.1 molar solution? Justify your answer with a calculation. So 1 liter of the solution made in 13A above. So for 13A, moles equals the molarity in 13A was 0.716. Nope, no, it wasn't. The molarity was 0.596. And the volume is 1.596 moles. And then, or 800 milliliters, 1 molar sucrose solution. So again, mole equals MV. So we're looking at, oops, was this 1? Did I do that wrong? Oh, my volume was 1. Ooh, I did it wrong. Darn it. Notice that my volume was 1.20. So to show you again, because I messed up, here's my molarity, and my volume was 1.20. So on this one, moles equals MV. I thought I had too many number ones. So then I had 800 milliliters, 0.8 liters of 1, which is 0.800. So 0.596, going back to over here, 0.596 times 1.2 is 0.715. Oops, I said a number I didn't write. 715 moles compared to 0.800 moles. What's the question again? Which has a greater amount of moles of sucrose? So the greater amount of moles of sucrose is this. So 800 milliliters of 1 molar. Okay. Which has a greater amount of moles of hydroxide ion? 500 milliliters solution A, or 650 milliliters of 1 molar B. Okay, so first of all, I want to point out that this has 2 hydroxides in each one. So let me change my color again. So on this one, moles does equal MV again, but I'm going to double that concentration. So my molarity is 2 because I get 2 hydroxides, and my volume is 0.650. Oh, welcome to my flippity dippity in my mind. Come on, you can erase it. 0.650. That's 1.30 moles for calcium hydroxide. 500 milliliters of solution made in 13B. So 13B, the molarity was 2.37. So moles equals MV 2.37. And the volume here is 500 milliliters or 0.5. So 2.37 times 0.5 is 1.19 from 13B. So which has a greater amount of moles? Here's my answer. So that would be the calcium hydroxide. All right. Which has a greater amount of moles of nitrate? 50 milliliters solution made in 13C or 130 milliliters of LiNO3 solution. So again, we're looking to make sure that we have 1 NO3 negative in there. So greater amount of moles, so moles equals MV. So the molarity of this guy is 0.185. I don't double it because I don't have 2 nitrates. and my volume is 0.130. 0.185 times times 0.13 is 0.0241 moles of nitrate in LiNO3. My other one is going to be 50 milliliters, so moles equals MV, so let's see, 13C. We had 1.42 molar, and my volume was 50, which is 0.05. 1, 2, empty spot, 3. I have a feeling this one might not win. 1.42 times 0.05 is 0.071 in 13B. So which one won? 0.071 won. Oh, please don't. Going too fast? Let it rest. It rested. Oh, I took it with me. Okay, hopefully that'll go away. It does. Student collects gas over water using the apparatus shown above. Right away, I have to remember, subtract pressure of H2O, because I forget that all the time. Answer the questions that follow about this lab experiment. Okay, so unknown gas. There's to open up a tank. Start it off here. We can read it. Explain why the water level inside the collection tube and outside the collection tube needs to be at the same level. Okay, so we talked about that before. So if they are at the same level, P in equals P out of tube. Whoops, I put tublet. It's an interesting word. Explain that the pressure of the room is the same as the pressure of the gases, assuming A is true. Force pushing H2O in equals force pushing H2O out. So equilibrium is shown by equal height. I don't like that question because it's kind of the same thing as A, but experiment with pressure room is not the pressure of the collected gas. Ah, you must subtract pressure of H2O for a given temp. How would you determine the mass of the gas delivered? So, I love my equations. I got a little more room over here. PV equals mass. Oh, that's not it. Okay, I'm going to go and write this. RT over molar mass is my first thought. But the mass, the gas, the mass delivered, it's not how you do that. How you find that is mass of the tank before minus mass of the tank after opening valve. So let's talk a little bit about what's happening here. So what happens here is it starts out where this is all filled up. Right? I turn on my little valve, and then this comes all the way down. So if I let this run for 10 minutes, well, the mass of it when it starts, it might be 120 grams, and the mass of it when I was done might be 118 grams. That means the mass of the air that, or whatever, unknown gas that we put in was 2 grams. So, molar mass of the unknown gas. So again, we're going to do PV equals mass RT over molar mass. So the pressure is 750. The pressure of the water at 22 is 19.8. Now, that means that, now remember, we're going to equalize the pressure. So 750 minus 19.8 is 730.2 millimeters of mercury. Now, I tell you, I don't think they're doing this in the class much anymore, but because I think they're just using regular units, 730.2 millimeters of mercury. Here's how you convert 760 millimeters of mercury in 1 atmosphere. So 730 divided by 760 is 0.961 for the gas. So this is total minus H2O equals the pressure of the gas I care about. Okay, so I've got the pressure of the gas. Check. Volume, almost 0.358. Check. Mass before and mass after. So I'm going to subtract these two. So 25.1 minus 24.276 equals M equals 0.824 grams. Should check. Temperature of the water. Oop. Trying to get me again. 22 plus 273 is 295. Check. R is a constant. Check. Let's plug it in and do these now. So the pressure is 0.961. Volume is 0.358. Equals my mass is 0.824. R is 0.0821. Temperature is 295. Molar mass is what we're solving for. Let's do the algebra. So 0.824 times multiplying these top ones times 0.0821 times 295. And then these are going to go down. So I'll divide by those. Divided by 0.961 divided by 0.358. And I get 58.0 grams per mole. Good. 5 milliliter vial contains 750 grams at 0. Calculate the pressure of the vial at 25 degrees Celsius. So, looks like we're doing it again here. PV equals mass RT over molar mass. Pressure, what I'm solving for. Volume, 5 milliliters is 0.005, 3 decimal place move in liters. Mass is 0.75. R is 0.0821. 298 Kelvin. Molar mass is 12.01 plus 35.45 times 4 is 141.8. And so that's 153.81. So P equals, let's do it, 0.75 times 0.0821 times 298. Notice I multiplied all of these guys. I'm going to divide by this and divide by that. Divided by 153.81 divided by 0.005. I get 23.9 atmospheres of pressure. Now that's a really big number, so I'm going to run those numbers again. I'm going to check to make sure my mass is 0.75. Yep. 0.0821. 0.0821. Temperature is 298. That's Celsius. Divided by the molar mass. That's the right molar mass. 153.1 divided by the mill volume, which is 0.005. And I got that again, 23.9 atmospheres. Okay. Gas has a vapor density of that. At 350, if a container of gas has a pressure of this, what would be the molar mass of the gas? So Remember how we said you can rearrange it, but density equals PMM over RT. And when you take this, if you solve this guy for mass over volume, you will get this. Okay? So I'm going to go ahead and run with that though. So 0.750 equals 2.22 atmospheres. That's pressure, right? Atmospheres are pressure. The density is this, grams per liter. What would be the molar mass? So molar mass is what I'm solving for. And R is 0.0821. So when I solve for molar mass, I'll have 0.75 times 0.0821 divided by 2.22. And I get a number less than 1, which is terrible. So try that again. 0.75 times 0.0821 divided by 2.22, 0.027. So PMM, there it is, over RT. This is what I get for not running my equation properly. So I forgot to put the T in there. So remember, a molar mass of something cannot be less than 1 because hydrogen's the smallest one. So I need to have 0.0821 and 350. So that means my answer is going to have to be multiplied by 350. My first one was wrong. So 0.75 times 0.0821 times 350 divided by 2.22, and I get 9.71 grams per mole. Like that a lot better. Good. Pressure in a 1 liter rigid plastic at 1100 was measured and recorded over time. Use the graph below to answer the questions that follow. So what happens? Pressure goes up. So that means I probably have more gas forming. Okay, I could be increasing the temperature, but that's it. Okay, so it's got to be more gas because the temperature was kept constant. All right, determine the moles of gas present in the flask at 5 minutes. 5 minutes, right here. Oh man, so this would be 0.62. How terrible is that? So it's a little bit of 0.65. So P equals 0.65. Looking above, V equals 1. T equals, was it 1100? 1100. So moles of gas. So it's just moles of gas. Oops, we'll let this settle in. So moles of gas, I don't need a special PV equals nRT. I just need PV equals nRT. So PV equals nRT. 0.65. Oops, I wrote 0.55. Volume is 1. Solving for N. R is 0.0821. T is 1100. N is 0.65 times 1 divided by 0.0821 divided by 1100. I get 0.00720 moles. Determine the moles present at 20 minutes. So it's going to be almost exactly the same, only the difference is this is going to be pressure equals 1.01. So everything else is the same. PV equals nRT. Pressure is 1.01. Now, I'm going to look and see if this is collected over water. Because if it's collected over water, we got to deal with some stuff here. Nope, it doesn't say it's collected over water, so we're okay. The volume is still 1, but I put V for some weird reason. Volume is still 1. Solving for N. R is 0.0821. T was the really hot 1100. And then do the math. 1.01 times 1 divided by 0.0821 divided by 1100. 0.0112 moles. So notice how it's quite a bit bigger, right? Because it had a much larger pressure. So let that catch up. And again, all of these numbers, the volume and the temperature, that same volume and that same temperature came from up here, where we had a volume and a temperature given. All right. I think that, see, and I thought that might have been the last one. Okay, so here we go. We got another one. Last one. Okay, H2O2 plus alkyl negative yields water plus chloride plus O2. Student investigates the reaction between water and NaOH. Notice how we got rid of Na because it's always soluble, which is represented by the net ionic equation shown above. Student decides to produce 40 milliliters of oxygen, so 40, I'm going to put 0.040 liters. Oops, I'm going to write it neater. 0.040 liters of oxygen at a pressure of 0.998. Oops. And 298 K using the reaction represented above. The student uses the equipment shown below. Student sets up a 250 milliliter Erlenmeyer flask fitted with a one-hole stopper. The flask is connected to a 50 milliliter gas collection tube that initially is completely filled with water. So it starts out up here. We can read that. Good. Calculate the volume of 0.8 molar H2O2 that the student should add to excess NaO3 to produce this. Okay, so what this is asking me to do is find the moles. So I'm going to start with PV equals nRT. So we looked at the pressure. So we produce 40 milliliters of O2 at a pressure. Okay, so we're producing 40 milliliters of O2 at that pressure and temperature using the reaction above. So the hard part here is to figure out if I have to subtract the pressure of water now. Okay, now it doesn't give me the vapor pressure of water, so I'm kind of stuck on that. So I'm going to assume that we're going to do that and make that adjustment. So the pressure is 0.998, the volume is 0.04, 0.998. They wanted to make 40 milliliters, 0.04. We're going to solve for N. R is 0.0821. Temperature was given to us. And that's 298, which I can see right here. So N is 0.998 times 0.04 divided by 0.0821 divided by 298. N equals 0.00163 moles of O2. Okay, calculate the volume of that molarity. So looking up here, right? So this is a balanced equation. So it's a 1-to-1 mole ratio. So that means I'm going to need 0.00163 moles of H2O2. Okay. So I'm going to change my plan a little bit. So moles equals MV. So 0.00163 equals 0.8 times V. V equals 0.00163 divided by 0.8, which is 0.00204 liters or 2.04 milliliters. Either one is fine. Okay. Student added the amount of H2O2 aqueous calculated in A to excess NaOH. However, instead of producing 40 milliliters of O2 gas, the volume indicated the diagram below was produced. So remember how I said it was going to make too much because we got to subtract the vapor pressure of water? So this right here made, let's see here, there's 5. So this is 6. So it made 35.65 milliliters. So based on the diagram above, what volume was produced? This is 35. This is 36. Notice it's a little lower than that. So I needed to have another decimal place. Assuming that all the gas in the tube is O2, calculate the percent yield of O2. So they tried to make 40. So I'm going to check that number again. All the gas in the tube is O2. Oh, percent yield. Okay, So I was supposed to get 40. So I was supposed to get 40, but I got 35.65. So percent is part over total. So it's still forgetting let's just subtract the vapor pressure water. So this one's making me sad. 35.65 over 40 equals 35.65 divided by 40 equals, I forgot my times 100%. Times 100. And I get 0.89, oops, not 0.89, get 89.1%. Is the assumption that all the gas in the O tube is correct? Explain. No. H2O evaporates some. Pressure of H2O must be subtracted or be considered. All right. In the upper echelon below, V1 equals V2. Answer the questions that follow about the apparatus, assuming there is no change in temperature throughout the experiment. Okay, so just a little baby checking it. 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14. I got 14 colored ones. 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14 white ones. And then the end, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. So I'm going to assume that's going to be 14 of both. Okay. How can you tell in the initial vessel there are equal number of moles in V1 and V2? I counted them. How would the initial pressure in V1? How would the initial pressure in V1 compare to the initial pressure in V2? It would be the same. Equal moles equals pressure at same T and V, which I said the volume was the same, they said the temperature was the same. How does the average kinetic energy of the particles in V1 compare to the average kinetic energy of particles of V2? It's the same. Temperature is directly proportional to average kinetic energy. What information is used in order to compare the speed of the particles? So remember, speed, Ke equals 1/2 mv squared. We need the mass of particles. We have the kinetic energy. Right, so if I want to compare this, I need these two. It told me the kinetic energy. So all I have left is that. How does V1 and V2 compare to V total? V1 and V2 are half of V total. They told us they just moved the barrier and they told us they were equal volumes. So what happened to the pressure of the gas in V1 once the barrier is removed as shown by the final container? V1, so I'm going to put pressure of V1 goes down. I rewrite pressure of V1. P V1 goes down because the volume for V1 goes up. When the pressure has to be one's pressure moves, it doubles. So what happened to the pressure? So I could also say the pressure of V1 is half because volume for V1 doubles. Both of those are okay. You can't quite tell which one they're looking for. And we're done. Woohoo! Let's put a little bit of stuff there, wasn't it? So I hope you can at least figure out what you were stuck on or what questions to ask in class. So, toodles.